Good afternoon. It's my great pleasure to invite Professor Subroto Mukherjee, a very close colleague on a major effort together, and also a wonderful person, and I think he'll regale us with stories, who has kept the mood of the people struggling with the challenges ahead. Intolerable limits so that we are still operating. So Professor Subroto Mukherjee is a senior professor at Institute for Plasma Research. He was the dean till recently. He is currently head of LIGO division and dean administration of IPR. Earlier he was the head of FCIPT division, which is basically a separate division which looked at plasma applications that could come from the Institute of Plasma Research. And before, as he was saying, at a minute's notice, he had to decide to dump all his 12 years of work and take on a new challenge of the LIGO India. The contribution that should come from IPR, which is substantial. So he is, of course, a very well-established scientist. He was the first recipient of the Booty Foundation Award for Outstanding Contribution to Plasma Sciences in 2008, and is recipient of the Humboldt Foundation Fellowship in 2001. And he received the Vasvik 2016 Award in the field of materials engineering, and was elected fellow of the Gujarat Academy of Science in 2016. 2018, he was elected fellow of the Indian National Academy of Engineering. So Subroto leads, Subroto I have seen, because I have not seen him in the FCPIT time, but we did meet, interestingly, just a few months before that. But he, leads a group by example, and, it's an amazing story of success in this project that has come out from this Institute for Plasma Research in trying to, make sure that LIGO India is built in time in India. So without further ado, let me invite Subroto to give us colloquium.
So good afternoon to all of you. Yes, thank you, Tarun, for inviting and all the arrangements which are made. I had a fantastic lunch and then a fantastic coffee, so I'm awake. And why I put these two pictures, the first one on the left side, you will, so he is Dr. Senthil Raja, he is Dr. Milind Govardhan from DCACM. Senthil Raja is from RRCAT, and Tarun, as you can make out, and myself. This post is supposed to be the 00 crossing of the LIGO. So when we have the laser, this interferometer, 00 crossing is this post. So we thought that let us touch this, and it is still like that. So we have to make, and from here one side it is 4 kilometers and another side it is 4 kilometers, like that. And this is my team at IPR. And this is taken about a year back. Now 2 more people have joined and 2 more would be joining. And we discussed that the day we get the cabinet approval, we'll have a lunch in Barbecue Nation sponsored by me. So it is here. And so we have listed down which are the incidences where we'll go to Barbecue Nation during lunchtime. And so this is when we celebrated that day. LIGO, of course, everybody knows. This is mostly astronomy, astrophysics. Everybody knows that this is one of the very ambitious mega science projects being done in India. Most mega science projects are done abroad, so we have contributions abroad. So this is being done, and this place is near Hingoli in Maharashtra. So I'll just touch a little bit of LIGO and then ultrahigh vacuum, which is the main thing, and what we have done to tell you that the vacuum part, what is our confidence level and what challenges lie ahead. So this is the Big Bang. This is taken from the Big Gun Samagam. This was done, and Big Bang, and somewhere over here we are, 13.7 billion years. This is the present Earth. And we have, in this so-called space, we have galaxy, star, nebula, black hole. and these can merge. Of course, everybody here knows about that Einstein gave a theory of general theory of relativity, and it predicts various things. One of them is that there will be stars or neutron stars, black holes and things like that, which are few times mass of the sun. They will merge in some fashion and generate gravitational waves. And these are the properties. So with speed of light and transparent to matter and initiate distortion. So this is a simulation. In fact, initially when I thought that this is actually a real image. But then somebody on simulation and then I heard the story that this lady, after this simulation became so popular, she got a lecturer or assistant professor job in a US university. This also I heard. Anyway, this is a simulation of two black holes which got merged, makes another black hole. And the entire thing that there is a distortion of the space, which is space-time around here. This is from the LIGO, USA. This is the signals. There are two places, which is one of them is the Hanford. So you see something, and then as the merger happens, you see, and then beyond the merger, this happens. So these are two places, Hanford and Livingston, which is about 3,000 kilometers away. One is on the north in the Canada border, this one, and this is very down south, very close to Florida or New Orleans city in that there. And this is the day the discovery happened, the one which I showed in the previous one, that is on September 14, 2015. Two black holes of 29 solar mass and 36 solar mass, they merged, made another big black hole of about 62, and the difference of 3 solar mass is what gave rise or propagated in the universe as gravitational wave. And this is done by using a Michelson technique. I'll go to a little bit in detail later on. The displacement that was measured is of this order, 10 to the power minus 18 meter. And it is about 1,000 times the size of a proton. So that is the sort of size one would have to measure. And even the LIGO India will have to be designed exactly in that. So it is the third LIGO detector or observatory being built in India. All three have to work at the same configuration, at the same level of efficiency and everything. So this is a very important factor, but we have to measure. Now these three gentlemen got the Nobel Prize, Rainer Weiss over here, and then Barry Barish and Kip Thorne. Out of which I had a chance to interact online, that is through video or this thing, with Rainer Weiss, because he's a person whom, if I am asked to make this vacuum vessel, I'll make it in a different way. And he made it in a completely different way. Then I realized that is why he's Rainer Weiss and I am Subroto Mukherjee. He made it in a completely different way, completely economically he made it, so that even in long term, the running the machine to get maintaining ultra vacuum, that cost is also very low. So this is something which I learned, how he has chosen the material, how he decided, which I'm going to come in my talk. Now, for all of you, this is extremely basic. We know about a Michelson interferometer. So light comes from a coherent source. It gets split into two parts. One goes here, one goes here. There's a mirror which reflects it back. Then there's another mirror which reflects it back. And then you have here interference fringes. This typically we did it in our MSc, finding wavelength of sodium light using this technique. So these are some constructive interference and destructive interference. What would be that thing? Now if we have only this, then the signal of the light, which goes here and comes back, and this goes here and comes back, the amount would be very low, the interference patterns. So what happened is that if you have to measure something which is very small, let us see how it is done, or what it is being done now. Now simple Michelson interferometer if we have, and if we have a wave which comes over here, it is going to which, like a gravitational, which distorts space-time. So because it is distorting the space-time, so this mirror would move when this is coming towards this one, or the other way around, this will move away or this way. So like that way, this will continuously happen depending on the motion of the wave. So this displacement which happens is because this space-time has been sort of distorted because of gravitational wave, and the mirror has moved from this location to this location, and we see some changes over here. So gravitational waves, typically the ones we are interested is in this order of this one, 10 to the power 3 hertz, like 1 kilohertz to below, to about 10 to the power minus 17 hertz. So more and more massive black holes would be merging. The lower would be the frequency of their merger. So this is what, currently we are all in around less than 1 kilohertz to about 10 hertz in that order, what we are measuring. So suppose we are interested in doing a measurement around 100 hertz, because it's moving at the speed of light. We have about lambda about 3,000 kilometers. So if we have to measure h, which is delta L by L, we require a very large L. So typically a lambda by 4 is 750 kilometers. Now, so each of them should be of that order. So one of the ways to make it lesser would probably be in putting a Fabry-Perot cavity inside a Michelson. This I understood as that this is probably a very new concept brought at that point of time when it was first proposed. So the light actually reflects many times inside this, and there is a small amount of, say, leakage which happens. So suppose it reflects here 400 times, and then it goes out. So, and continuously light is coming from here, that is from the laser. So everything is bouncing 400 times, and suppose, and one then comes out. So this will continuously go on, and that will happen even when the gravitational wave is propagating. Normally it is kept in such a configuration that you don't get any signal. So it is dark. It's only when there is an oscillation happening, you start seeing the signal. So it is the other way around, not that you want always kept to get a signal, always kept not to get a signal. So that is adjusted. So this Fabry-Perot cavity, so this is a very critical mirror in this configuration, the same over here. At this, of course, is also very critical. And these are about 40 kg of mass silicon, 40 kg one mirror. And this is balanced by another 40 kg. That is for optical and as well as alignment purposes. But this is about 40 kg single crystalline silicon with a coating on top of it. Please.
So, one thing is like you are increasing the effective path length by multiple reflection. But since there is a leakage in the cavity, like after like couple of reflection also there will be some leakage, right? So is there like that will create any problem or?
No, it is leakage because it is continuously coming or continuously leaking.
Mm-hmm.
But suppose if I send say 100 units of something from this side, it will go 100 units will bounce back 400 times. If it bounces 400 times, one will go out. So 99 will stay. So like that way, this so-called this power, if you start somewhere around 100 watt, it will be extremely high power over here.
Okay.
In fact, that is one of the very critical things, that while this is on, nothing should fall, like even dust from the chamber, from your beam tube wall, which is like this. Nothing should fall in the laser path because it will be immediately ablated, then plasma, and we don't know where it will go. So this is continuously coming. This is continuously getting reflected. Continuously leakage is happening. Only thing, but it is set to that you see actually dark over here. It's only when they move relatively with each other, because of whatever I showed, that this moves, this contracts, you see the interference patterns. There's also a chopping of the laser which is also done.
The details in the sense that the experimental setup exactly, so you want an optimal path value, path difference, right? I mean, optimal paths of 750 kilometers. So you say you're bouncing it up and down. But of course, this is happening all the time, right? When it's off, it's really on in the sense that
It is
yeah,
on.
it's on. But of course, it could leak at any time. So you could also have a much longer path length as well. So you will get, you can in principle find different, if you have a signal going through, you'll get it at different path differences, right? You'll get it at different, you'll get a full interference pattern, right?
Let me see. See, this
I mean,
is
that's, I guess,
this
the
is your
path
signal.
length is not fixed.
This is your signal, and it is not that only one frequency at a. I am assuming that when we are detecting one merger happening, it's only one merger we are. It is not that exactly at the same time we are also receiving signal from another merger happening somewhere. So at the given, now this is what is your signal actually looking like on the detector. This is something which is not processed. The process signal would be a little bit different. Many of the spikes will not go away. So that is where Kip Thorne gave his arguments, that you make templates, and if the noise is this much, then what will happen type of an argument.
I guess the question is that the path length, yeah, which path length will be actually, how do you know what the path length is since there's a leakage?
The LIGO is a broadband detector. So when he calculated it 750, he took 100 hertz. So it goes from 100 hertz to almost like a factor of 10 more. So that's why the path length, how much it varies doesn't matter, because you need sensitivity at all the frequencies in that band. So this lambda by 4 is 400 hertz. But
So
you look at 1000
at least
hertz.
get that much. You
Yeah,
want to get
so
at least
it was just to
sensitivity.
say that a 4-kilometer detector
Right,
will not be in that range at all.
So
But
all
that's
the
about-
other, if it
Yeah, yeah.
bounces more than that, it'll be outside of your sensitivity range also, I guess.
Yeah, so
Actually,
it is,
if
the
you take
broadband
this one-
sensitivity is from up to 1000 hertz.
See, currently what we are, or LIGO is actually measuring, they are all in this order, 10 to 100, 10 to 100 1 kilohertz in that order. Suppose, and the solar masses are like 20, 30, 40 type of solar masses. Now suppose we get something which is 1,000 times solar mass. This thing will not detect it at all. You require another range, you require more lengther, or you have to change the wavelength or do something else. In fact, there is a space program, that is what is being told also. It will come, LISA, by 2035 they will start sending, where it will be, I think, some 1 lakh miles or something. Okay. So this is Hanford. It's in a very dry place, and Livingston. It is much like India. It rains. It is near south. And when I saw this for the first time, my experience was that I was sitting in this sort of building and looking at this length, there are 4 kilometers. How can something be so straight, 4 kilometers? Because it has to beat the curvature of Earth, because the light is going and it has to come back. And in between 4 kilometers, Earth will have some height. It has to beat that curvature. And also, not only that, there's other problems. To reduce any kind of vibration from surroundings, already we are taking care that there will be no heavy movement like transport vehicles and things like that, or mechanical movements. That is the nearby region. But finally, even after suppression, if you get something over there, you have to ensure that your vibrations which are inside are extremely less over there. So there are various types. So finally it comes that the mirrors are hanging. So that mirror, whatever I showed, they are all hanging. So everything is hanging. If something is hanging, then obviously the gravity of the Earth is pulling it. So this is the center of the Earth. This is, suppose let us assume from this place. Suppose, let us have this. This is 4 kilometers. Suppose with respect to the center of this point, this place is somewhat down, and this place is somewhat down. And here are this mirror and this mirror hanging. After all, when you hang two mirrors, so this is being pulled by the gravity. So this is like this, and this is like this. So you have to make it like this. So you start getting secondary problems, and you compensate that, you get another problem like that way. But in spite of all that, LIGO USA detected the signals in 2015, and since then many such other mergers have also been discovered. So these are, Vargo has already come. Their sensitivity is a little bit less than what Hanford and Livingston has. And this is a 3 kilometer. Their configuration, the Michelson technique is same, but otherwise their configuration is a little bit different. Their vacuum levels are also different. And Kagra has just started operating. They have certain problems related with water droppage and things. But this is below a mountain, the Japanese people have done. So this is the Hanford, like as I told, northwest of USA. This is Livingston. This is Virgo. This is a Geo 600. It's a much smaller compared to them. And LIGO India, which is being planned, we are working on. And Kagra, Japan, still under construction, a little bit. It is going towards conclusion, but it seems their efficiencies are a little bit on the downside. So with this introduction to LIGO, just telling that this is what the entire thing is all about, I'll come to the main part of my talk, which is the ultra-high vacuum. Now, as I understood during lunchtime, there are some people who are experts in ultra-high vacuum, gone to even below 1 into -9 milliwatt. Only thing is that in small volume, like in a TM, HRACM or other devices, we typically work around below -9, like 1 into -10, -11 millibar. Again, because electrons have to go from a source to detect something. You know that a TM or a HRACM or other such equipments, the maintenance is a very big thing. Like you require air conditioning, you require a isolated grounds, means mechanically separate, power has to be very stable and things like that. So even on a very small volume, much lesser than 1 meter cube, the restrictions are extremely high just because the equipments are very sensitive. They're measuring nanometer level or even lower than that thing. And also you require in large volume an accelerator, synchrotron, and now LIGO also. Of course, there is a debate about this number, but typically 1 into -8 millibar or below, pressure is considered as ultra-high vacuum. Most people consider. You may or may not agree with me, but this is what is generally accepted. Usually the vacuum systems have to be very clean, free from contaminants, even hand impression or even other. Even while talking, whatever thing comes out from the mouth, if they have a little bit of water, that also may evaporate and deposit. The vacuum system, gaskets, O-rings, whatever is used, they should withstand baking, which is a major requirement in many of these ultra-high vacuum systems. And usually they are electropolished, but not for LIGO. And this is a major change which probably was proposed by Ray Wise, and he proved that you can actually get ultra-high vacuum in such large volumes without doing any electropolishing. Again, if I am asked to do, I will do electropolishing, because that is what I learned all throughout my life, that if you want to get good vacuum, you have to do good electropolishing. But not for LIGO. Usually this is obtained using a combination of mechanical, turbo, ion pump, cryo pump, all put together. And pressure is measured using a combination of various gauges. And gas composition measured with RGA. And hydrogen is the dominant gas in UHV conditions along with water vapor. So this much is a general what is UHV. Now let us come to ultra-high vacuum. It is a major challenge. I will not call the most major challenge, there are other challenges also. So this is a typical, this is basically from the vacuum system requirement document of LIGO India. It is being taken. So there are 6 chambers, and I'll show the chambers how they look like later on, which are marked as green. 2 more dark green, because these are added for LIGO India. And then this blue chambers, 5 of them. And the first picture which you showed, you saw with me and Tarun touching, this is this point, BSC2 as it's called. This one. In this configuration, this is this one. this big chamber, the middle point over here. So this is the formula which tells that how the strain noise would depend on the pressure, and this one depends. So this basically tells that as low as pressure you have, it is better. Now, the total volume that has to be evacuated in LIGO is about 10,000 meter cube, and pressure have to be maintained below 10 to the power minus 9 millibar. There is no additional gas being put from outside, but whatever comes out, because we have a lot of optical and other components, either fixed or hanging, from the outgassing from the walls of the chamber as well as the tube material, they are your main load, and they have to be moved out. Now, what is desirable for LIGO is that you have, these are the most of the gases which are present at that value. Hydrogen is 1 into minus 9 millibar. Water vapor has to be at least 1 order lower than that, 1 order. Then the rest of the things are there. So it is not that one has to get minus 9 millibar is enough. You also have to maintain at least this ratio. One hydrogen below, water 1 order lower, then the other things even 1 order lower, like that. So LIGO has a nomenclature, like they call this as HAM chambers. This one called horizontal access module, and these are called as BSC chambers, or basic symmetric chamber. Now, how are these chambers placed? This is again taken from LIGO USA. So the HAM 1, HAM 2, it goes here. Then there's a HAM 3, HAM 4 is here. Then BSC 1 goes like this way, and 1 goes on this way. And to connect this, we have this very mode coupler tubes, then spools. You can see something called as gate valves, which are extremely big. Each gate, and there are only 2 companies in the world who make this big gate valves. One of them is VAT, and another is GNB. And then there are the pumps which are called as long cryo pumps. There are certain changes we made in LIGO India just to make things a little bit simpler, and on the suggestion of LIGO USA. I'll come to that later on. At the end station, because this is all inside one building, this all, and then from here, 4 kilometers happens, and then you have another building here at the end of 4. This is the configuration within that building. You have a cryo pump over here, and then a BSC chamber, and there are some optics and everything. So all the major optics is all either in this building or this building or this building. On top of that, LIGO USA came with another configuration called as A+, and currently they are operating in the A+, which has an additional filter cavity of 250 mm into 300 meters long, which connects HAM 5 and HAM 7. So this is not here, this is taken from it is this one. These 2 chambers are additionally kept for LIGO India. The LIGO India's A+ configuration is like this, as of the moment. In USA, the configuration is different. It actually comes from here, goes here and goes 300 meters in this direction. So this is a change which we have as of the moment. Now, if you look at the vacuum equipments, this vertex is the place in the mid station where this crossing is there, the corner station. And then there are mid and end stations. These vacuum chambers are opened very frequently, typically maybe once a year or something like that, to change the mirror or the optics or something else, or either the hanging support has broken down or something. So these chambers are opened as and when needed. And they are all inside this building is a class 10,000 clean room. So it's already, and it's a huge volume of class 10,000 clean room with very strict specifications on the air conditioning temperature, like 23 degree plus minus 0.25 degree, something like that. You have to maintain the temperature. Even the wind flow should not disturb anything, both outside the chamber or inside the chamber. And whenever a chamber is opened, the chamber is engulfed with another thing which has a pressurized airflow to make it class 100 clean room. So then only the chamber is opened and someone wearing all those uniform will go inside. I will tell you my experience when I went there. After all the things, somebody asked me, there is a dress code for a person who enters inside the chamber and does something, and someone who is his assistant standing outside, giving him, okay, he tells, give me the spanner, I give the spanner. He removes something and gives him back. So there's someone who is holding it. And he asked me, suppose the spanner drops from your hand on the ground, what will you do? I told, I'll pick it up. That is our response. He told, you will not do that. It will lie on the ground. When you are leaving the room, you will carry it outside, because it may pick up something from the ground, maybe a small dust particle. So this mindset has to also come, which we have still not gone into that level. It's a mindset that you don't touch something. If it falls, let it fall. Like another thing which is in LIGO, we have been told that inside this building, not to use anything which is having a mechanical movement on its own, like electric, like a drilling hole and something like that, or some machine which will tight. Even the cranes over here, crane has many moving parts. They are all oil-free or grease-free. The reason is that any moving part will obviously cause a little bit of heat, and some oil or the lubricating medium may evaporate. It may hang around the building and may enter one day inside the coating or something on your chamber when it is opened, on the mirror. So these protocols have to be sort of built up by working more with that. So these vacuum systems, these chambers, they are opened more frequently, and they have flanges, fittings, viewports, feed-throughs. They have very big covers, and end covers are double O-ring sealed, and this is a source of large water load. And this is one of the, after you clean up everything, each time you open, because people are inside, a lot of moisture anyway goes out because they are breathing and things like that, along with water. So a lot of water load is there, and you cannot bake them too much because you have optical components and signal components, electrical things which will bring the signal outside the chamber. So you cannot bake them because they will start evaporating otherwise. So we have to see that how to introduce, and so it takes a lot of time in getting again the vacuum in these chambers if they are opened. And between many of these chambers, as you can see over here, there is no isolation gate valve. So you open this one, basically this and this is also exposed to atmospheric pressure, though they are closed otherwise. Real challenge is in this beam tube. Though there are no active components inside the beam tube, so 4 km here and 4 km here. But Ray-wise designed this, and of course engineers implemented it, that it will never be opened. So once made, it will never be opened, and also it will never be pumped out unless it's absolutely necessary. There's a leak or something. It will not be pumped out also. So once made, 4 km will remain. Whatever pumping is all because we have opened the end station or at the corner station, we have opened some chamber. This beam tube should never be pumped again. Now, please.
So, I'm saying this vacuum is going to be maintained all the time.
Yes.
But for the regular operation, do you expect the vacuum gradient, the pressure gradient, would affect the measurement sensitivity?
Yes.
Then
so
what is the tolerance in the vacuum gradient that it's not going to affect? I mean, how much that within which you need to maintain
this beam tube, which is that 4 km, has to be below 1 × -9 millibar always.
But practically that is challenging, right? I mean, to maintain that within that gradient.
But it is maintained.
How
Okay.
it is maintained?
Let me tell you.
Yeah.
So this is 4 km. At the end of 4 km, you have a gate valve. Then you have a cryopump. This is a cryopump which is inline cryopump. So any water vapor, then after the cryopump, you have another gate valve, and then your BSC chamber or this chamber. If I go to the configuration, it will become more clearer, this one. See, you see this gate valve, this is a gate valve. It's a 1.2 meter diameter gate valve. And as I told, only 2 companies makes in the world, GNB and VAT make this gate valve. Then this is a long cryopump. Then this is another gate valve. The beam tube is from here 4 km. and this from here, it is 4 kilometer. At the end of 4 kilometer, this is sitting. This gate valve is sitting. And then you have a cryopump, again a gate valve, and again a chamber. Suppose I want to change something in this chamber. The mirror has cracked, let's assume. So I'll open this one, and so this is a class 10,000 room in which we will have a tent, which makes it class 100. I will open this chamber, somebody will crawl inside and will change the mirror. Or some electrical signal has broken, will repair or replace it. Though we have maintained the temperature and its humidity, everything is maintained, but because people have entered inside, this has to be then pumped from atmospheric pressure down to about 10 to the power minus 7 millibar using conventional TMPs, turbopump based stations. At 10 to the power minus 7 millibar, you will open only this gate valve. Whatever water load which comes, it will try, because this is maintained at 10 to the power minus 9, it will try to move there. This cryopump will actually condense it. It has a, I'll come to that later on in the detailed slides on what we have done. So this traps the water vapor. This pump is still running, the TMP is still running over here. Once this comes to the order of something like 10 to the power minus 8 millibar, this one and this both together, then this one opens up. Now here is the beam tube which is 4 kilometers, like here 4 kilometers. That is at minus 9 millibar. There is no pump connected with. So this minus 9 millibar is now like a pump for this amount of load which comes from here. Water vapor is trapped here, and whatever gases which came, they get spread over here. Now my job is done. Now I am waiting for the signal to come. If a signal in something happened somewhere, it is coming. So what will I do? What will I have at this point of time? I'll be having cryopumps which are located here and here. So these cryopumps are going to run only, because we do not want any mechanical pump to be on when we are ready to detect signals, just because of vibration. So only cryopumps are on. And cryopump will maintain below 10 to the power minus 9 millibar everywhere. Inside these chambers, it typically is below 10 to the power minus 8 millibar, something into minus 9 in that order. Because it takes a lot of time for the trapped gases and as well as outgassing and water vapor to come. So here the pressure would be higher than the remaining beam tube. So ion pumps are always on. I'll put it in that way. Ion pumps at the ends are always on. The real challenge is here, the reason I'm telling is this diameter of this particular beam tube. I'll come to more details later on. 1.2 meter diameter. My height is about 1.6, so it's like this much small diameter. If I am asked again, I will make it out of about 6 mm thick stainless steel. Ray-wise made it 3.2 mm and put stiffeners at regular intervals, so that though this is maintained at minus 9 millibar and this is only 3.2 mm thick, it doesn't, go inside because of the pressure gradient. And this is 4 kilometer long, perfectly straight, even beating the Earth's curvature. 10,000 meter cube of volume, about total inside surface area of 30,000 centimeters square, and all welded metal constructions. So all are basically welded. They are 20 meter pieces which are welded and welded and welded. So 400 such pieces are there which are welded in this direction and this direction together. It is, after it is done, it is baked for 150 degrees for 4 weeks in vacuum. That is at the initially, and it is isolated by a 50-inch diameter gate valve, as I told you. Now here come some more things, like what I call it as how the supports are given. Normally because these are 20 meters, so at the end of 20 meter only our supports are there. So they have, LIGO USA has two kinds of support. One is a fixed support. So this fixed support is basically fixed over here. And then there is a support which is called as a guided support. And in between this guided support, there is a bellow. So every 20 meter, there is a guided, so there is a fixed support, then 20 meter a guided support, having a bellow, and again 20 meter, again a fixed support, like that way. Now what is the difference between these two supports? The fixed support, of course, the name tells it is fixed. It cannot move. The guided support is one in which there is a bellow. Now why do you need the bellow? Because when you bake it for about, like what I said when you bake it 150 degrees for 4 weeks, continuous, you do the baking, this will try to expand. But because this is fixed, it cannot expand on this side. So it will try to expand on this side. And it's same with this part. This part cannot expand on this side because it is fixed to the ground. It will try to expand. So bellow gets compressed over there. And how this baking has been done by LIGO? They passed a DC current. Because this entire thing is welded, so you pass a DC current through the entire pipe, and because of ice resistance, it will be I square R heated. And you put a cover on top of it so that the heat doesn't escape. So this is a very, very detailed way of Ray Weiss is doing these calculations and everything, how much current is needed and everything. And they were very lucky. They had required power supplies from Fermilab, which they took on loan, or they availed that power supply, and they were able to bake it and give it back. For us, that's not there. So we have to still get such a huge power supply, which would be able to bake 2 kilometers intervals of 4 kilometers, total 4 kilometers on one side at 2 kilometers. Now this is something which we got from the LIGO USA. How did they make these tubes? Now, as you have seen that they have two different locations. One is on the northwest side, another is southeast side. So how do you make these pipes? How will you transport them? These are 20-meter pipes. This is a real challenge for us as on today. How will you transport 20-meter pipes? And that too in a very, very phased manner. Because some will have bellow and some will not have a bellow. You are going to weld it only at the site. Our site is very remote. It's a very small place, not having wide roads like US. So what US people did is that they found out a nearby town, about 20-25 kilometers away from the site, where they made these pipes of 20 meters. And they transported in a normal truck, long enough, but with a special packing, which allowed class 100 air only to go inside. So each of them is something which we either have learned something or we are yet to learn. So what did they do? This is just a flow chart, and we have to make an identical flow chart for our vendor. We'll also have to make. So the raw material comes, a pipe is getting made, then it gets cleaned, then it is baked and is leak tested, and finally it goes out. So these are the various things. Based on that and our interaction with our industries, we worked out a similar flow pattern of the work, which I'm going to tell at the end of my presentation. So this is what they did, the LIGO USA. So this is the coil, that is the 3.2 mm thick. It comes in the form of a coil. It's about 760 millimeter long, so about this much width, a coil of 3.2 mm thickness. And this coil gets unrolled over here, and then this part of the machine makes the edge preparation. So you have to slightly taper the edge, and then it goes through a machine which bends it. So it's like a sheet of material which goes like this, and then it bends, and it bends like this way. And their welding is happening inside. And it comes here, and when it reaches a 20-meter length, it's precisely 19.8 meters, you actually cut it over there. So it's a continuous process with intervals in between. Do this much, cut, it goes there. Then in some of them, you weld a bellow over here, the same bellow which is supposed to take the compression. So this is being done at the factory. And a cleaning process happens, a very elaborate cleaning process. We followed the same cleaning process, and we faced a major challenge. The chemical which they used, Mirachem 500, we could not find it in India. And on the Mirachem 500 bottle, they don't write what it is. Composition. And even if they write the composition, we don't know whether that's the right composition. So we did a lot of trial runs in vacuum technique as well as in Godrej to find out what would be very close to that. And somehow, with the support of the vendors as well as our own engineers, they were able to find something very close to that. So their cleaning is also very different. That first there is a steam which cleans inside, and then the steam follows. Then there is this isopropyl alcohol, and so there is a step of cleaning. After the cleaning is done, so now it is fine. You have to pack it immediately, and packing cannot be done with something which itself gives a lot of dust. So you cannot put a wooden packing and things like that or anything. You have to pack it in a a particular type of cloth, which has some ports which allows air to go in, but have certain sizes over there. Now, what does the beam tube look like? So this is only a picture of a person standing, so you'll get an impression. This is not exactly symmetric in the center, so it is slightly off-centered. A person is standing. So as I told you, it is very close to, with the support like about my head. And this is the RCC structure, which is like a dome structure, which is being put. First look at this picture, and then I will come to the other pictures. These two gentlemen fixes the pipe. This is the opening of the pipe. So this is this one. So this is the class 100 clean room. So these people only fit one portion of the pipe with the other one. Fit means they're putting tags. So it's not a very permanent welding, but it's a reasonable welding. They call it the field fit up in class 100 clean room. This is here. Then there is a person who does a welding, because each piece is only 20 meters long. And then there is another person who does the checking, whether there is a leaks or not. See, there is no vacuum checking happening. You will only check the vacuum when you make 4 kilometers. And after making 4 kilometers, you find a leak. You will not be able to find the leak also, because you don't know where it happened. But the same problem, I interacted with some people and asked them, how did you do it? They told that their vendor also had the similar problem. They told, we'll do welding, everything, all as per the protocol. But vacuum responsibility, Caltech took the responsibility. In our case, we would like to put it on the vendor side. See, a vendor may tell yes, but then he will tell you, sir, I don't know how to do it. So this is a major step. Now comes this one. As you can see, this is in Hanford. Some snow is there on the road. This truck, they have made, of course, their US roads are much bigger. Only 2 20-meter sections are only going in one pipe. Only 2. So basically, you are only transporting air, because the weight is very less of 2 of them compared to what the truck can carry. But this is what they did. Then it gets mounted, this cover opens up, then enters here, and then it goes to like this. Now, because each of them is 20 meters, USA on an average did 3 pieces a day. That is 3 20-meter sections in one day, US did. I don't know what our vendors would be able to actually do it at site. But my understanding is that if 1 per day is very good. We may take time, but let us do 1 per day very accurately. Because if you have any mistake anywhere, either in welding or alignment or anything, it will become a very big problem to go back and rectify it. As you can see, this is at the baking, they had some covers. We have, of course, improved on this material and the cover much more as of now.
I missed what is the problem of locally checking the vacuum over 20 meters?
You are welding 20 meter with another 20 meter. That is at site. Suppose after 1.5 kilometers you have done, and now I am adding 120 meter.
Yeah.
How will you check the vacuum? That end is blocked, and this end is there. This is made in such a way because another 20 meter is supposed to come and you have to weld it. So there is no flange connection here that you can connect a pump and do it. Now, if every 20 meter you connect, you have to measure the vacuum. If you have to measure the vacuum, you have to go to -9 millibar.
Okay.
That will take 1
Then
week.
only you know whether the leakage at that level.
Leakage at that. So that is what I told. If I have mast, I will make flanges and weld and connect nut and bolt. But that is like you're increasing your capacity of maintaining the vacuum, cost goes up tremendously. And manufacturing cost goes up. But here it is all welding. And you can see that it is not in a very, the person is actually lying on the ground. And LIGO USA people in Hanford, they actually told us that you should practice a lot on lying on the ground and, crawling and things like that. And all for reasons which are needed. And they even told that we should have thing, not only lying on the ground, but with a small wheels. So if you have to move from here to here, somebody just pushes you. Not that you do like this and move from here to here like that. Now, what are the installation and setup challenges? Of course, there's a lot of optics and other challenges, detection, laser stabilization, and everything is there. But for vacuum purpose, there's 4 kilometer aligning, a 4 kilometer beam tube. And you can see the structure which is there. This is that RCC structure. So each time you complete a 20 meter, you do the fitment move, the welding comes, he moves, the leak checking comes, move. This RCC structure is also coming behind you. And he is putting. And he is sealing. So there's only a gap of 1 day. This is the US what they did. As I told, for India, if you do 1 per day, but perfect. I would tell Ki this is good enough. More than 1 is always better. But 3 seems to be too high for us. Okay. Now comes the last part of the talk. Till now everything is clear. Now, what do we do? So this is a picture made by my colleagues in DCACM. Now I just tell that LIGO India, there are 4 institutes responsible for doing the first science run. So making the first science run. Science run means basically making the detector ready enough to detect a signal. So this is an artist impression. This is one building which is already made. This is the site office at this moment. This is the so-called the corner station, and this is 4 kilometer on this side and 4 kilometer. This is called as the X arm, and this is the Y arm. This is the LIGO nomenclature. And then there are other offices over here. And this is in the Hingoli in Maharashtra. So if you go to this, what is the temple? Aunda Nagnath. Aunda, there is one of the Jyotirlings in Maharashtra, very close to that. So the work is broadly divided. Site acquisition, development, civil infrastructure is DCACM's job. This is a unit of Department of Atomic Energy. IPR, vacuum facility, vacuum control monitoring, interference control, and data acquisition. This is our job. We are a aided institute under Department of Atomic Energy. RRCAT Indore, of course, the major part, which is interferometer, detector, 3rd generation upgrades. Basically, the entire laser and optics is there. And IUCA site identification characterization, in which Tarun played a big role. Then the science data, and finally our interface with the scientific community is through IUCA. Let me come to our experiences and then I will tell on that.
That's fine.
I am going to touch upon that.
I'm just curious whether because of transport is such a difficult.
I will come to the challenges. And where a lot of, even crazy ideas are needed, as well as fantastic ideas are needed. And where things are a little bit, yet to be decided. So LIGO India, when completed, will add to the network of existing detectors and improve localization of the gravitational wave sources. So there is a slide at the end I have actually kept after thank you. This is a slide of Rana Adhikari. I don't know whether people are familiar with Rana. He's a Caltech a professor, very much awarded for his contribution on gravitational waves. And in fact, currently he is in India somewhere. He may be coming, I don't know it, but he is in India now. So he has done some calculations which told that if you have the third one in India, how it will help in narrowing down the location from where the wave is. The fourth would be even better. But along with the two USA, LIGO USA, and then this one, the third in India, it will be better in the. So this improves the localization of the gravitational wave sources. So what are the challenges? Large volume chambers. Like this is one as I showed. This is the beam tube. This is of course the beam tube with the cover over there. So even if you are standing on the crossing and you are told to see 4 kilometers, so you 2 kilometers far away you see a building, and 4 kilometers some far away you just see a small dot like that. Right? And that's what the other BSC chamber is there, which has some optical components. Then you have these cry pump and large gate valves. And this is the vacuum, as I told. The selection of the steel for fabrication of chambers and beam tube. It's normal stainless steel 304, but with some conditions. The hydrogen has to be below some ppm value. Sulfur has to be above this and below something. Because one enhances the ductility, one enhances this, one would finally impact the vacuum. And it has to be hot rolled, annealed and pickled, HRAP. So many people may not be familiar. Normally what we see is all cold rolled, annealed, cold rolled, whatever we see as sheets. Hot rolled, annealed and pickled. So it comes to you, it doesn't look like stainless steel. It's a bit rough. You'll feel the roughness with your fingers. That is needed. Then integration of these various chambers. These chambers, one thing good about the chambers, they have flanges at the end. So there are also, couplers and things like that. But you have to put these chambers in a very precise location. And as I told you, the total volume is about 10,000 meter cube. And data acquisition control is one thing. And this is the thing over there, pressure. So this is the vacuum SRD, vacuum system requirement document approved by LIGO for LIGO India. And there is a mid station where we have proposed to put 2 gate valves. And that is also under discussion, that whether we should have it or not have it, because we have some recent experience with VAT is not very good with the 1.2 meter gate valve. And then this various other things. So actually this distance is 4 kilometers in this drawing. This is 4 kilometers. Again, this is 4 kilometers, like that. These are the 2 chambers we made from this company Vacuum Techniques, in Bangalore. And this was done during the COVID period. So in August 2021, we actually delivered it we made it and we delivered. And I was surprised that this was done without any delay. Normally, if any delay happens, we put LD, 5% is deducted. These vendors, because probably they didn't have any much work at that time, and they put their best effort and they delivered in time, which is, I consider that as very remarkable. Normally, fabrication people ask for extra time and things like that. Now, this is the one chamber. This is the BSC chamber, inverted and mounted on this. And these are my 2 colleagues, Sunil and Vijay. And this is the hand chamber. And in the first transportation from Bangalore to Indore, because it was supposed to go to RRK at Indore, where they will make all the internal supports and put it inside and operate in vacuum condition. This is full size, 1:1 size vacuum chamber. The truck, the truck, while it was entering Madhya Pradesh, the engine got damaged. So 3 days it was on the road. And it was raining heavily also at that time. Then when they reached Indore the previous night, and our people were already there, and we told them this is the road to be followed and all those things. And only after 10 p.m. trucks can enter a city. That's the rule in many cities, including Indore. They entered, instead of an overbridge, that she took a turn earlier. and hit the level crossing. Level crossing, you have that rod which maintained the height. So this portion actually hit the rod. So there was a police case. And the truck was taken by the police along with these chambers to the local police station, and the driver was in jail for 4 days. So we were seeing the chamber from outside, but it was a police case. So after 4 days, his owner from Bombay went, and he was free, the chambers were free, it entered. But because it got that chamber, it hit the top part, so one of these flanges, this one, because it is now inverted. So this flange which is here, that hit. And because that hit, there was a mild crack in the welding joint. But on the outside part, not on the main chamber. So that got replaced. So there was an insurance, and the vacuum techniques made another flange, and then everything got replaced. So in the first transportation, we learned many things about transportation. So,
How much are each of these, how much is the cost of each of these chambers?
these two chambers, the basic cost is just slightly less than 4 crore, both of them. But today, if you ask vacuum technique, they will ask double of that. Because it was a very challenging thing. Even we realized after doing, the tolerances needed are very high. I'll tell you one thing. Are you able to see this port? I don't know whether you're able to make out that this port is not at right angles to the circumference. Now the reason is that this port and its opposite port, so all are like a cylinder. You have ports which are all at right angles. But one port, 2 ports are like this here, and 2 ports are like this. The suspension is through this. But the entire thing inside is actually suspended. So it must be suspended somewhere. So there is a vacuum isolation along with a support over there. So these 2 ports have to be very perfectly aligned. Otherwise, what is coming from, see, this is isolating port. It is outside is atmosphere, inside is ultra-high vacuum, and components are hanging on it. So these 2 ports and this port have to be exactly the same over there. So these are the challenges within some accuracy of sub-micron level and things like that, on a diameter which is more than 2.5 meter. I'll tell you the problems which we envisaged for the first time. We have never, at least I have never made systems like this in earlier. When everything is cold at room temperature, you measure a dimension, and after welding, then it becomes cold, dimension changes because it has expanded and contracted, and a new dimension has come up. So, and LIGO used extremely highly tolerant in terms of tolerance. They have not taken the rough tolerances, they have taken extremely smooth tolerances. So we took, even after making a lot of machining and things were needed. Anyway, my friends put a lot of effort. In fact, they were there at all the time. And this person once actually drove his own car from Ahmedabad to Bangalore because going by flights just started and people thought it was too risky to travel by flight. So they went on car and things like that. So this is at the shop floor working. These are some laser tracking techniques used for looking at dimensions. So this is the chamber. As you can see, it is 2.6 meter internal diameter, height 5.2 meter. This is slightly smaller, and these are various thicknesses and over there. Then comes the next thing. You have to operate at a pressure below 10 to the power minus 9 millibar, or assume something into minus 8 millibar with load. How will you do it in the factory? If you tell the factory, show me minus 9 millimeter, minus 9, 10 to the power minus 9 millibar, he will tell, okay, sir, I am connected the pump, we wait for 2 months, you will get it. But he will charge for it. So we, with a lot of effort and a lot of discussion, mostly with LIGO USA people as well as some Indian experts, we decided that we will have the leak rates same as what is accepted in LIGO, but our vacuum measuring levels would be 1 into minus 7. So if a factory which shows that leaks are not there and shows that you get this vacuum, the rest is only we have to wait for pumping. Otherwise, he will just pump and he will charge money for because we are occupying his premise. So this also took us a lot of time for us to understand that how do we accept this one. Now comes that, okay, we are telling a steel has to be like this and these are the properties. How do you know that? So first thing is that we measured an outgassing setup. And this funding came from a DE project called TDCB, Technology Development Capacity Building Phase, through RRCAT. So Director RRCAT, my counterpart over there, Dr. Senthil Raja, they of course supported these activities in a big way. So this is the chamber which is used for measuring so when you make a coil, you do all the baking and everything. Now you want to know what is the outgassing rate of that. So you use this kind of setup. So the empty chamber, these are the rate of rise from. So this can actually measure hydrogen outgassing in this order, which is actually extremely low value. This is the empty chamber. You put any load, it will be higher than that. We have to get something in the order of 10 to the power minus 13 millivolt liter per second per centimeter square. You know, an outgassing of hydrogen in that way. At the same time, all the data has to be logged into using a protocol which is very close to what LIGO USA uses. So if we give them a link, they should be able to see what we are doing, what kind of readings we are getting. So we have a CDS. Fortunately, the CDS, the control and data systems, is also IPR's work. So we both support each other. Once those chambers are made, we realize that there is some money available and we have to work on how to make a large cryopump and something like a vacuum vessel, 20 meter. And that was a presentation which we gave in Ayuka. Tarun was in Ayuka at that time. After that, it went through the COVID thing came and many things happened. And this was finally approved. Now, why we did the cryopump? I'll show you a cross-section of the cryopump. This cryopump's job is to have this chamber. I have put new things in the chamber, which is giving a lot of hydrogen, which of course pumps are taking care. But at the same time, it is also giving a lot of water vapor. This water vapor has to be condensed. So condensation means the surface which is condensing water vapor must be a good thermal conductor. At the same time, it has to be low cost. So aluminum is one of the chosen candidates. Even LIGO USA has used. But if you have to make a vacuum chamber, then stainless steel becomes your choice of vacuum chamber. So aluminum sitting inside in a container or in a vacuum vessel, which is at ultra-high vacuum, and inside this aluminum we have liquid nitrogen filled from outside. So at one place, an aluminum to stainless steel joint will come. Somewhere. You do it outside, inside, wherever. How will you make this joint stable? Stable means if it leaks, your liquid nitrogen from here goes into the vacuum chamber and hence to your beam tube. US people did brazing as a technique. But what Fred and others told that this is always, they are always have a very thing that it should not fail. So we started looking at alternate techniques of that, which is also repairable. My main worry is that if something goes wrong, we should be able to repair it. If we are unable to repair it, we are in deep trouble. So my friend N.C. Gupta and Rakesh and others, they put a lot of effort, Arnab, Sunil, a lot of effort in trying to develop that joint. And a local vendor in Ahmedabad finally made that joint. And that is the one which is currently over here. This is a 20 meter. It is basically 2 into 10 meter. This is again on a floating support. These are fixed supports. And this is, this 20, of course, it has many ports over here. This uses a different technique of fabrication. Its dimensions are same as beam tube. Only thing it is not made in that way. I'll come to that later on. So these 20 meter sections are 10 meter into 10 meter. 10 meter, 2 of them. And this is how. Now what happens is that they were hot rolled, annealed and pickled, and then they were air baked. The moment you air bake, they look like brownish in color. It looks like as if there is rusting has happened. But this is not rust, it is air baked, it has brown color. Even in LIGO, if you go, this will be brown in color. And now how is this made? Are you able to see this joint, a straight line here? You are able to see. Basically what happens is that this is where it is made in this way, and then, so you have small cylinders, and you join the cylinders to cylinder and weld them. This is a very slow process. LIGO did spiral welding. We are not doing spiral welding because spiral welding of this dimension 3.2 millimeter thickness stainless steel is not available in the country as of now. You will get thicker ones of other steel over there. So we did 10 meter, and this you can see Brian over here, I'll be here, Atul is here. And we had spent a lot of time in trying to make these two pieces, like these two, one piece and one piece like this, weld and be very perfect in dimension. Then there's a bellow, how it is formed. This is the gate valve from that, like that. And then we have stiffeners, exactly like what LIGO used. This is the entire vessel which is for the cryopump. Again, Brian is there, and my colleague Sunil, Ritesh, Rakesh, then Ashwini, Arnab, they're all here, and the other people from the company. So everything over here is extremely big in size over there. The cryopump is actually in diameter even more than the other chambers over there. So I'll run the video. This is the complete system, as you can see from here. These are basically, there's a local factory which made this kind of tapes, which are extremely, they can heat it, as well as insulation cover is there. So this is this big gate valve that you see from here, and this is the cryopump, which is from this side. So this we named as this facility as LI Vista, LIGO India Vacuum Integrated System Test Assembly. And this is how it stands if you look at it from on top over there. Now let us look at what we have done. Material is SS304L, ID is 1.24 meter, this is the diameter. Sheet thickness 3.2, these are things which we have done. We joined them by making 10 meter section having I seam and C seam. Basically I is like this and C is like circumference. So many small cylinders welded together. And then we did all the standard tests which are needed for this one. And currently it is running at 5 into minus 9 millibar, and it will reach 1 into minus 9 once we feed the cryopump, which is here on this side, with LN2. Now you require LN2 to take the water vapor out over there. But our main thing that we will be reaching that in 5 into minus 7 millibar from atmosphere, we reached it within 100 hours, which is, it tells you the graph that if you follow this graph, you'll reach 1.9 millibar, 1 into minus 9 millibar at some point of time. So all that is there, it is done. Only thing that this is not there, a spiral weld. And this is the cryopump. This is exactly 1:1 size cryopump. And the major thing which is over there is that this is aluminum passive thermal shield. There are various constructions inside. And here we have gone up to 7 into minus 9 millibar. And we'll get again 1 into minus 9 when we put the liquid nitrogen over there. A major part is, of course, taking all these data and integrating it, which is what currently the LIGO CDS team is doing at IPR. And these readings are all to be shared online with whoever has the LIGO protocols can access them. So these are the CDS various activities. CDS not only supports the vacuum, but it also is supporting the RRCAT activity on the control and data systems. So CDS's group is sitting here. One side is the detector, another side is the other people, Ayuka and others, which would be there. So the challenges that we took undertaking are 1:1 size, the BSC chamber, HAM chamber, and the cryopump. These are 1:1 size. Prototyping on the 2 into 10 meter section with same diameter and thickness as LIGO. Bellows also of same thing, and we measured pressures which are available. The leak rates are as per LIGO, and the vacuum is lesser than 1 into -7, which are accepted conditions. Based on all the interactions that we had, we realized that we have to work out a flow chart and give it to the vendor, whoever makes the beam tube and the chambers. So this is for the beam tube. Wherever you see a different color, these are the places where we are coming into picture. We are giving a certificate for the vendor to go ahead. By we, I mean the project team. So this is the raw material it comes, so there is a testing involved here. Then the outgassing, qualification of the coupons from air, again we are involved. And then it goes like this way, over here. Then 20 meter, he makes pipes. 20 meter, we do again a non-destructive testing to see the leaks and everything are not there. And then this way it goes, fitting, welding over there. And then perform again a leak test on the beam. Now let us come to a problem. We don't have roads which are like in USA. So if a vendor decides that he will not, even if he makes a nearby place, say 20, 30 kilometers away, nearest city, big city is Nanded, which is about 70 kilometers. He makes there and he transports this. The last 2 kilometers is the problem at the site. So he decides either to make it exactly at site, that is one choice for him. Another choice is that he tells, no, you have made 10 meters already, I'll make 10 meters. 10 meters you can transport on Indian roads, no problem, even a small road also. But then your number of welding joints at site increases. And so number of all this will increase, your testing and everything will increase. Or the other way, he may tell, if I'm making 10 meters, why do I make somewhere nearby? I can make in Bombay, Pune, Hyderabad and transport it. This is where I asked Fred Rabb, one of our from USA, asked him that what we should do. He told that if you expose this so-called pipe, which is made of very thin material, our transport usually goes 200 kilometers a day, a truck, 200, 220 like that. It cannot go more than that I mean big trucks. So if they go, so if you, suppose you travel from Bombay to that, making in Bombay and transporting, you will require about 5 days or so. So 5 days, the top part of the beam tube gets more sunlight, so it gets heated, so it expands. And in the night, both come at same temperature. So after some time, there's a possibility that it will more look like a, like an egg. The bottom side is like and top part is like. So he told that you have to be very careful that you don't overexpose. That is the reason in LIGO, USA, they did it in a city which is very nearby, 2020. So they load it and in another 1 hour's time they're at site, like that way. So this is something which we have to still come to a conclusion. 10 meter versus 20 meter at site, remote location, far location, nearby location, over there. Of course, a vendor's choice would be also. Also remember that this is a very precision welding job, so high quality manpower and retaining high quality manpower may not be so easy in a remote location. You may, Bombay, Pune, you may be able to retain them. This is the vacuum equipment which is mostly for the BSc and ham chambers. Here the requirements are not that much, mostly on the raw material, and then comes the pump down, leak testing and vacuum demonstration, and then final acceptance at the site. Here, because these are independent chambers, you have enough time to repair things if anything goes wrong. So this is the same picture, artist's impression. This is Brian, just to give you some idea of, these are my friends, Rakesh and Arnab, all 5 feet 6 inches. So he's like 1 feet more. So this will give you an idea, sort of chamber sizes and things like that. This is Dave and Brian when they visited Godrej. So Vijay is here, I am here, and some other colleagues are there. And this is the day when we went. So it was announced that on 11 May 23, that the means online approved this thing, PM, Honorable PM, giving it to the, inaugurating virtually the LIGO India project. So we didn't go, we were in our IPR seminar hall. We took a picture. So if you are interested, there are of course various books. These are general books. But there's an article written by prototyping the vacuum chambers by IPR in the LIGO magazine. You can get it, or Tarun has it, or some, it will be there. There are some other papers also. So this is the site. There is a dam over here called Siddheshwari Dam, the bluish in color of this place. The place is up and down, this place. And this is the two sides of it. So acknowledgements, my colleagues from LIGO division of IPR, they are the ones who did all this work. I used to just go and stay for 2 days and come back, but they spent months at the factory. And of course, my director, who has been extremely supportive of whatever we wanted to do. He has been giving manpower, support, funds, and everything, whatever is needed. Chairman and members of the Project Management Board and the Science Management Board. The Technology Development Capacity Building project of DAE, which is through RRCAT. A lot of funding that we have received for doing these activities. DST actually gave a partial funding through Ms. Ayuka. And I'm very grateful because Ayuka director, that time Somak, allowed that money to come because we bought the SolidWorks license with that money. It was not from the other one. And Fred Rabb, Dave Wright, Brian, Rana Adhikari, and Dennis Cohen, they were there. But John Feit has been extremely clear about ultrahigh vacuum, very knowledgeable. And he wants to come when we do things, only things that we have to tell him a time. Brian wants to come, Dave of course comes nearly every year, once at least he comes. Brian is ready to come. So thank you for your attention. If there are any specific questions, I can answer.
Thank you very much, Professor Subroto Mukherjee, for the wonderful talk. And we could learn so many interesting details and very interesting stories about the very ambitious LIGO India project. So I'm sure there are questions.
I was wondering, is there any kind of lifetime test that it is done, because this is a very long-term, sustained for a very long time?
Lifetime,
is there something like that?
No, we do only analysis, basically extreme case or worst case scenario analysis. Analysis all on computer. There are no real tests in that sense. But we are following exactly like, I remember once I told 3.2 millimeter. Actually, it is 3.23 millimeter with a tolerance in thickness of -0 plus 0.07. Now, what it means is, I take a sheet, I measure its thickness. It may be 3.23 here, it may be 3.4 here. After all, it's a material, so it is allowed to, and that too in a width of this much. So LIGO requirement was 3.2 to 3.3. The vendor who made for them, he told 3.23 is what he will do. -0. -0 means on the lower side it will be 3.23. On the higher side 3.3. With this tolerance they made. When we came to India and we started hunting, we found that it is very difficult. 4 millimeter is available. So we had again a discussion with Ray Wise. He told choose 4 millimeter. But 4 millimeter comes with its own problem. Your weight increases. 3.2 becomes 4. So it is 20% jump. So weight increases by 20%. Raw material cost increases by 20%. But then your weight on the support also increases by 20%. Again, because the mass of the material has increased, your baking also has to increase. So we are actually, in small volumes you may get it, but in larger volume, maintaining a perfect tolerance at this level would be a real challenge.
Thank you.
You said mechanical pumps are not operated when it is in operation.
Yes.
But cryo pump also has cryo compressor as such. So that vibration coupling is not an issue?
No, there is no cryo pump, ion pump.
Ion pump, okay, fine.
See,
right.
this cryo pump which I am telling we are developing, we are naming it cryo pump, but actually it is a vacuum chamber at 10 to the power -9 millivolt, which has an annular aluminum ring,
Right.
basically another aluminum chamber, which is filled with Ln2. Only thing which you have to be very careful is that if because of some reason things get heated inside, or a molecule of water vapor comes and sits on it, it will condense. The moment it condenses, it will give its heat back. So one of the one or few liquid nitrogen will bubble out, because the heat is going away from here. That bubble will give a vibration. So vibration should not come on your detector or your anything which is used for detection. So there are springs to damp. You will be extremely unlucky when the gravitational wave comes if there are bubbles at that time.
And one more related question is, this long vacuum tube is supported at different places.
Yes.
So they are all vibration isolated or?
Yes.
Okay.
They are vibration
Each of
isolated. Vibration and electrical.
Okay.
You also have to be electrically isolated from the ground.
Yeah. Oh, final question if I can ask.
Yeah, please.
So when you have 3 LIGOs, different places, so the maintenance is coordinated because these things will require periodic maintenance. So obviously, what is the arrangement like?
The arrangement in both the 2 LIGOs, they operate exactly in the same. So when both are down, both are purposefully down. If there's an upgradation in one of them, same upgradation is done in both of them. Things like that. Yeah. But in a case of LIGO India, I don't think we have gone to that level of understanding.
Right.
But obviously, the management structure, maybe including scientific management structure, will probably be one. I think there's a PAC. You are a member of that one, so he can tell you the slightly more detail about that part.
Sure. Thank you.
Sir, one question regarding dimensions. You said midsection X and Y alone is 4 kilometers. When we are looking at one representative diagram that showing X and Y arms, and then additional peripherals which makes the entire system. What is the overall dimensions of the X and Y arm itself when midsection alone is 4 kilometers? I think it is not to scale, I think.
No, it's not to scale. See, the cryopump which is inside this building to the cryopump inside the end building, 4 kilometers. This is 4 kilometers. 3980 to be more precise.
Yeah.
And then inside the building you have another nearly like around 12 or 13 meters inside the building.
So that total 4 kilometers itself is achieved through some 198 sections of this 20 meter.
It is 4 kilometers on one side, so 20 meters is each section.
Yeah,
so you
198.
require 200 in this side and require 200 in this side.
Yeah, and then regarding bibliography, what are references, we'd like to have that slide once more so that we can make note.
You can actually take this slide, no problem. But I will. And where is that?
PPT, in that one slide had shown, maybe we'll just first.
No, I can show it, no problem.
Yeah.
This one?
Yeah.
So, can I?
Now there is a LIGO India science paper, instrument science paper has come. I am not very sure whether it is in DCC or not, but it's a LIGO India science paper. Please, sir.
So each arm, whether this is thermally isolated? Is it it's exposed to with the metal, right? This is the metal.
Metal, yes.
During the day, then you have uneven heating of this. On the top, you have more heating and then less heating at the bottom.
I mean, after installation?
After installation.
After installation, there is RCC structure, not air conditioned, this 4 kilometer. It just kept with an 2 RCC structure with some polymer material in between so that it doesn't allow rainfall and things like that. And this goes 4 kilometer.
Is it also going to help in maintaining the temperature around the?
It will maintain, it will nearly. Actually, there is also discussion which happened earlier in the US that they put this thermal insulation which was used, was actually kept over there. Both from this one as well as, like it will, if there is a noise coming, it will damp the noise. But then later what happened is that the rats started making their house in that. And then along with that all the problems, then they removed that.
Okay.
But our what we have used in this 20 meter, it's much more compact, both the tape that we use for heating purposes as well as the insulation. It's a completely different material being used, and they guarantee a long lifetime.
Okay,
And it is very easy to install.
Right. Now, one related question to the earlier one. What is the plan on synchronizing with other LIGOs?
They will all be having the same, I mean time synchronization?
Yeah.
And they will all have in the same time.
It's the same way, it's a plan for this one also.
So all the three. All the three have to operate simultaneously. Then only we can do the detection. If something is coming, we will be able to detect it.
Okay.
In fact, they are the other one, the Virgo and Geo, and they all are in sync with all of them.
Any more questions?
So you had mentioned this a different way of preparing the stainless steel from the normal. You said it's hot annealed and the surface is rough and all that. So what is the reason why we need to use that as to other? Because one would think that more rougher there is chances for dust and things to be compared to a smoother.
Though what happens is now is that they actually see after 20 years. So they're operating, they made all the vacuums in 98 to 2000. Today sometimes they see that if they hit the beam tube somewhere, they can see without the laser, they can see that some particles are falling down. So a large part of this, whatever that oxide layer is formed, will form small things which will fall down with time. What the idea was, if I understand correctly, what Ray Wise and his colleagues' ideas were that they would try to prevent the hydrogen present in the steel. I mean inside, not the bulk volume. Inside the steel, their outgassing has to be reduced. Outgassing. It has to be so less. Even first of all, you do baking and all those things. Water vapor, hydrogen, you do everything. But whatever is stored inside, that so-called 3.2 millimeter thick, that will come out very slowly. Would you put a barrier over there so that it reduces over there? So we have a problem means over there, because like if you increase from 3.2 to 4 millimeter, which is what the gentleman asked over there, this is also another problem. My total volume increased, weight and other factor is one thing. Amount of hydrogen stored there also increased, so it will also come out. That is the reason you cannot make a, say, 8 mm thickness wall and you cannot make a cylinder, because it will have double of that and it will come out.
Thank you.
Any more questions? If not, we thank again for your wonderful talk.
Thank you, madam.
And I would request our director, Professor Tarun Shoradeep, to give a memento as a token of appreciation.
Thank you. Great. It was really great.
Thank you. Very nice.
Told what you told your engineer, if there is a leak in the beam tube, he checks to lock it.
Yeah.
Put his engineer back in the beam tube and pop it up.
We invite you all to the tea outside.